Hi everyone, welcome to the Colloquium. I'm happy to introduce Jane Gao, a professor here in our department, to talk to us about random graph orders.
Thank you, Sam, for giving me the opportunity to talk in that seminar. So today I wanted to talk about something about random graph orders. And this is research work that I did with Anna Kumar, who was URA last year. So this is something really recent, and it's still a project that's going on. So it's not completely finished. The main purpose of this talk is to first, of course, I want to share with you. But the second primary goal was actually forcing myself to make progress before the day of the talk. And obviously, the second goal was not progress as much as I wanted, but it's something to share. So I wanted to talk about how this research got started, and then how this field sort of plays with other fields that are related, and then what we discovered, what we have learned from this. So the story actually comes from this part. I think about 1.5 years ago that Karen sent an email to the whole department organizing a study group on causal set theory. And I received that email, but I didn't read it correctly. I misread this UNS and swapped them as a transposition, which apparently is very common for combinatorialists. Anyway, I thought it was casual set, and I thought it was some kind of funny set system that people invented and just do it for fun. So I went to the talk, and then the first talk was, of course, a shock to me because it's something about relativity theory. Anyway, I stayed for a bit longer, and then I started to feel, well, there's something interesting, and especially it goes into something called random orders, and then I started to realize that it's connected to something that combinatorialists studied in terms of enumeration of partial order set and so on. So I wanted to spend some time talking about this, and then what we learned about dimension of random graph orders. All right, so since my story of my research, it doesn't work with one button. Yeah. Starts here. I'll talk about causal set first. There's some, anyway. Okay, so what is a causal set? It's basically, mathematically, just means locally finite partial order set. What it means if you take two elements, and there are finitely many elements in between. So as the upper set of one and the downside of the other one. In physics, they say x is smaller than y. What really it models is that x lies in the path light cone of y. All right? And then the physicists want a model, and of course, probabilistic model, to model the universe, time-space universe. And what they wanted is some kind of sequential model. So you add events in the sequence into your model, and every time an element add in, you want to decide whether it lies in the light cone of some previous events. So in this example, like 1 is first generated, and you generate 2, 3, 4, 5, and then a relation like that says 2 is in the light cone of 1. Okay, then it requires a bit more to be a realistic physics model, but you don't really have to understand, at least for this talk, what those hypotheses are. But what's important is it's some kind of sequential model that generates a partial order set. This doesn't listen to me, so let me go this way then. So what I want to say is that the random graph order apparently is a classical sequential growth model. Actually, so the primal one that has been used to model this partial order set. So I'm going to talk about what is a random graph order. All right. I assume everyone knows GNP. So GNP is a random graph that you have n vertices, and typically consider them as labeled vertices. So vertices are labeled from 1 all the way to n. And then you connect two vertices independently with probability p. So that gives you a graph. And now you want to convert it to a partial order in this way. So if I is less than j in natural number order, and they are adjacent in the random graph, then in the partial order, I is less than j. Now, of course, in order to make it partial order, if I is less than j, j is less than k, you have to make I less than k, right? So you take transitive closure of this random graph, and then you get partial order. Here's one example. Because of the limit of the space and my time, I only draw 5 vertices. So this is G5P. And I always draw the lower vertices at the bottom. So this is the graph. And then when you write the partial order, for convenience, I write the direction to go from smaller element to larger element. But here, because 1 is less than 3, 3 is less than 5, so in the resulting partial order, I have to go from 1 to 5. So there's another relation, 1 to 5, that's being added. All right. Okay. So one nice thing about this, and it's also something really, really desirable for physicists, is that I can define it on all the natural numbers. And this, obviously, you can do that, right, as a sequence. But of course, here you want p to be fixed. So it's some kind of number, 0.1 or 0.9. However, this model is more interesting for combinatorialists when you restrict the number of partial order to be a natural number n. So if you take this model and restrict to the first n vertices, you immediately go back to this partial order. Another reason that's really, at least for combinatorialists, why we care about a fixed n is that now I can make p as a function of n, whereas if you want to define it on the whole set of natural numbers, this is not meaningful. And I will see that allowing p to be a function of n will give you interesting thing to study. Okay, and fixed p actually very often, if you're familiar with random graphs, it's boring. Okay. So since we're talking about now random partial order set, I would like to deviate a little bit from the random graph orders, because even though random graph orders were more recently discovered as a way to generate causal set, but just as a study of partial order set, they have been studied much earlier, and there are random models already for partial order set. And especially if you want to randomize something or think about some kind of distribution on partial order sets, the most natural distribution is probably not from graphs, but for uniform distribution, right? So the first model, of course, is the uniform model, and that comes from counting. So if you want to study anything from it, of course, the first task is to count how many partial orders are there with an element. This follows from classical results by Kleitman and Rothschild in 1970 and 1975 in 2 different papers where they improved the count, the number of partial orders of n elements. When you take the logarithm, you get something like this. So this doesn't really give you the asymptotic result, but it's enough to give you some insights into the structure of a uniformly random partial order set. For instance, with high probability, uniformly random partial order set has 3 layers. This can be seen as somehow not very nice thing if you really want to model the universe. Right? We wish to have more layers of like kind of events. So that indicates that probably you need to, not thinking about uniform, but maybe inserting some kind of parameter, making it a bit more interesting. And that's this one. So instead of everything appear uniformly, I'm still consider uniform model, but now I'm going to restricting the proportion of pairs of elements that are comparable, and that's rho. Okay, so among this with specified row, how many partial order set or elements are there. So similarly, I can define a quantity like this, right? So this is like Rothschild's result. And then what they get is 1 row equals a half. This S row is a half. But now what about the other row? And when you look at this quantity, if you have seen some statistical physicists paper, you probably see this is something very similar, look very similar to what they typically study. Looks like this counting, right? It's like a partition function, taking logarithm, scaled by something like a local degree kind of thing. And indeed, it actually does come from statistical physics, trying to study some kind of local three-wise particle interaction of some gas model. So in that paper, this quantity was analyzed up to this range, which covers which is before a half, is it? Oh, the typical Rothschild one, sorry, I want to say, that actually the leading term here suggests that the comparable pairs is around a quarter. Yeah, it's around a quarter. So their result actually covers the range, a quarter, but a little bit more than that as well. And then what's interesting is it doesn't change the value as here, which is a half. And then Kleiman and Rothschild continued the research and studied the value of this quantity when rho is smaller, between 0 and a quarter. And then they found a phase transition right after a quarter. So for smaller rho, this is an entropy function. And then you probably guess what's happening at the other end. This is something interesting. So it's the research was carried by Promel, Steger, and Terrace, 2001. What the picture shows is that actually when you go above 308, it goes through an infinite sequence of phase transitions. And in particular, well, this is the plot, right? So this is about the harmonic function and the constant, and then it goes through different phases. And in particular, it indicates that the structure of the partial order set will change from 3 layers to 4 layers and 5 layers at each critical row. And there are infinite many phase transitions in a sequence. Okay, what's interesting, at least to me, is that although this is not the classical sequential model, it doesn't satisfy the hypothesis over there, but it does indicate that restricting density, which is the number of comparable pairs, is something that you can somehow adjust to make interesting models for studying. All right, so that's the message from there. Another model that has been studied, which is different from random graph orders, is the one by Peter Winkler in 1985. It's a model that you somehow restrict the dimension of random partial order. Since we are going to talk about dimension, so I think it's convenient to actually define their model, and along the way we actually know what is dimension of a partial order set. So how the order work is you take 2 uniformly random total order, and then take the intersection of the 2. Actually, this is 2, and then you can take k of them. So you can take 2 or 3 or 5, okay? So in this example, I take 2 on 5 elements. The intersection is basically for any 2 elements if both directions appeared in these 2, then they are incomparable. But if their order are consistent in all of those linear orderings, then they are comparable. So for instance, if you look at 3 and 1, 3 is less than 1 here, and it's less than 1 here, so of course, it's comparable. Right? 3 is less than 1 here, but however, if you look at the 1 and 2, 2 is less than 1 here, but it's bigger than 1 on here, so in the intersection, they are not comparable. So then, if you're given a partial order, you can think of trying to find a minimum number of linear orderings whose intersection will give this partial order. And that minimum number is defined to be the dimension of the partial order. So in this example, the dimension is 2 because this is a realizer of this partial order, right? The intersection does give this partial order. On the other hand, it can be 1 because this is not the total order or anti-chain. So that shows the dimension equals 2. So is the definition of dimension clear? Okay, good. So yeah, Peter also proved a bunch of results like connected, diameter equal to 3 whenever the number of, so dimension is bounded for this model. Okay, so now let's get back to the random graph orders. So remember, this random graph order is starting from random graph GMP and then take the transitive closure. Why is it interesting to study this model? And in particular, why do we care about P as a function of n and sending it to go to 0 as n goes to infinity? So if you know a bit of random graphs, you probably know that g and a half typically behaves the same as any g in P when P is some constant between 0 and 1. And most people even don't bother to write a paper about g and P if they can write something about g and a half, because the proof is usually the same. And what it indicates is that there's no interesting phase transition at all when P is a constant. And many or most of the phase transitions that I have seen in my life happens when P is much smaller. And that's the main reason. And then for partial orders, it's exactly the same reason. So what we can see here is a picture that's a bit impressionistic. So it's a shape of the partial order. So you can see that passing some critical value P here, it looks like that it's formed by a partial order, and you put on top of a partial order and put on top of a partial order. It's called linear sum of partial orders. So that's the picture. That's the shape of the partial order with hyperbole, how it looks like. However, before that, you get a big, fat thing. So if you ask what this relates to the real world as a modeling the universe, maybe you can think of as the start of the universe and then contract someday and then start again and contract infinitely many times. But if you are really only care about the current universe, maybe this is more interesting, right? But the current model, if you only set P as constant, you just cannot live here. So you somehow have to think about a sparse regime where you see interesting phase transitions. But of course, for physicists, it looks a little odd that you fix the number of events first and then make P as a function of P, of n. So there's a bit of, I don't know, compromise, we'll say, or maybe an open question is really, can you actually make up really reasonable, interesting model that is sparse, but still realistic for physics? But we are mathematicians, so we don't really care about whether it's interesting for physicists. We are going to make P as a function of n for this talk, and then see what kind of phase transitions we'll see. So we'll see a few examples where you move from P to 0 to 1, then various phase transition will happen for different kind of properties. And in particular, this is some kind of brief review of things has been studied. So the research starts by Barrick and Elders in 1984 about the largest anti-chain in this random graph orders. And then somehow it was forgotten and then reintroduced by Alban Fries in 1989. And in that paper, they study various things, height, width, dimension, first order properties in general. And then 1994, along Boller-Bosch and Jensen counted the number of linear extensions. And all of those work are for P that's constant between 0 and 1. And then usually I just write P equals a half to represent P is a constant. Okay, then really for P, goes as a function of n was started by the work of Erdős, Kistad, and Trotter in 1991. But they changed to a different model, which is the bipartite model. Often in random graphs, people don't expect things to be so different when you think about G and P and G and NP, unless you're looking for triangles. But usually, if you prove something for G and P, and people say, well, certainly the argument you adapted, it works for the bipartite case, and then you don't even write something down, right? And I was really surprised that things are totally different for these two models in terms of partial order set. So here's the story. So first, in that paper, they studied the lower bounds, the dimension of partial order set that just have two layers. Right? Each layer has n elements. And the reason for that research is actually trying to prove a tightness of some upper bound earlier proved by Ferretti and Kang in terms of any partial orders, what is the upper bound of the dimension, in terms of the maximum degree. And degree here means number of elements comparable to a given element. Okay, and their work shows that their bounds essentially is tight. 1p is sufficiently large, so a little bit bigger than log n over n. And then in the same paper, they realized it's really just interesting to study this random model by itself, and they raised something like 10 to 15 open questions in the end of the paper, and I think none of them were answered today, just because it was really, really hard to accurately say anything about the dimension, and even not possible to say anything about the expectation of the dimension. So one of the conjecture that I like a lot is that if you look at the expectation of the dimension, what they conjectured is that when p goes from 0 to 1, it's unimodal. So it goes up and then goes down, something like this. Doesn't matter what the shape exactly is, right? I just write it like a mountain, but for different, in fact, what happens in the bipartite case, in fact, is very different from the non-bipartite case, but actually it does follow the same shape. So this is a conjecture, and this is what they proved in their paper. And as I mentioned, they only go somewhere around log n. I skipped this 1 plus epsilon at the top to be inaccurate intentionally. And then there's some kind of phase transition around 1 over log n, where here you increase by a factor of delta is maximum degree, and log delta, but then around this part it becomes n, so it becomes very flat in this range. So it looks like this, but it's very inaccurate. As I mentioned, I have a lot of approximate sign in this talk. What it means is what they really proved is lower bound and upper bound. And the lower bound and upper bound typically differs by at least a constant factor, sometimes more, logarithmic of n or something. So we couldn't say that, we couldn't exclude the possibility that it locally just oscillates. But over a long train, it looks like what they conjectured. It has to drop in the end. So it's actually very interesting. And this is another conjecture raised, that at the very end, how did they drop to 2, right? And it's not clear yet. Okay, so that's for bipartite case. And here is what happens for the non-bipartite case. That was finished in a sequence of papers by Bollerbush and Brightwell within 3 years. And then what they studied posts, which is this kind of structure, structural change, phase transition around this time. And they also studied the width, the length of the size of the largest anti-chain, and then dimension, for instance. And again, the range is 1p is at least log n over n. All right, so here's what they proved. And if you look at this, and then compare with what is in bipartite, you can see a big difference. And that's why I say it's really surprising in some sense. that we normally don't feel that these two models are different. But it is really because there are no graphs, they are partial orders. And in the bipartite case, you have two huge anti-chain. And these two huge anti-chain really changes the behavior of the dimension of the partial order set. All right, so you can see that it goes through several phase transitions, the dimension of the random graph orders, the non-bipartite case. And the research were carried in by different groups. But I wanted to talk a little bit of insight on each phase transition. So this is the first phase transition. It coincides with the structural change where this fat blurb partial order set suddenly becomes a stacked linear sum. And in the bipartite case, we also have a phase transition here. But that's completely for analytic reasons. Okay, so the function just somehow changes a little bit, behave a little differently there. Then this is the second phase transition. This phase transition can also be well understood. It's because that there's two trivial upper bounds for the dimension. One is the width, and the other is the Fourier counts upper bound. And the right at here, one overtakes the other. And it turns out that the lower bound proof shows that they're actually correct. So that explains the phase transition that goes up and down here. And then they conjecture that there is a third phase transition at 1 over n. And I encourage people to study that. It's why there's a third phase transition. This is well understood in random graphs. It's one of the most famous known results that right at p equals 1 over n, before that, then the graph are all partitioned into small pieces, and every piece basically is a tree. And then once you pass that point, then a good part of the graph all join together. The little trees start to join together and form a giant component. And inside the giant component, you have a lot of structures. Right? You have, for instance, you can find a graph with minimum degree at least k, for any k, whenever you make p c over n, when you send c a little bit larger. Okay, so this kind of global structure seems to, well, at least at that time they think that it should indicate a change, phase transition for the dimension. And then it should also indicate something should appear here for the bipartite, because it's exactly the same phenomena is going to happen in the bipartite case. So Arnav and I were just trying to understand how this joining of small components in the graph structure and also of the process structure is going to affect the dimension. Is it going to suddenly blow up the dimension from something small to something really large? At first, we did think that it's going to happen, but it's very surprising that it's not. All right, so before the phase transition, so when everything pieces, roughly speaking, is tree, then or contains one cycle, then Brightwell has a proof that he just sent to me in person that they can prove that dimensions are most 4. And what we try to prove is filling this gap. So basically, you can see that it doesn't matter this C if it's bigger than 1 or smaller than 1, but some kind of function, the dimension is roughly the maximum degree. And it's curly because it's not exactly. So lower bound, maximum degree over log of maximum degree. Upper bound is maximum degree times the square of logarithmic. So, but roughly speaking, it's like a linear function, and it goes all the way to connect where Erdős's result terminate from last time. And here, even though this part is this and this part is this, it's not indicating if there's a phase transition there, just because there's upper and lower bounds, right? So it's not accurate enough to say if there's actually a phase transition anywhere there. Okay, and then the second part is the thing that I wish to finish before this talk, but I didn't. But we think that the same phenomena should also occur for the non-bipartite case. So there's really no phase transition at 1 over m. The tree structure joining to a giant component doesn't significantly impact the dimension of the partial order set. Okay, so that's the main result. Since I have some time left, I will just talk about some kind of intuition behind the proof, not the proof itself. So let's talk a little bit about the lower bound. We use some idea from Erdős, Kierstead, and Schroeder, but in a much more simplified way. So their proof is quite complicated in order to really reach a bound that's tight, right? Remember, if I interpret their result, their final dimension should be something like this, maybe. The final dimension should be something like c times log c. And that proof definitely fails when you go to p that small. But if we only aim for something like c over log c, we can do a much simpler proof. So the idea is the following. If you have, you have some kind of elements. One is here at the lower bottom bar part, and the other in the top part that is non-comparable. So obviously, in some linear ordering of the realizer, you must put y before x, right? And that's called the reversed pair. So every non-comparable pair has to be reversed by some linear ordering. And the idea is that to prove every linear ordering can only reverse a small number of incomparable pairs. Then if you have total number of incomparable pairs, we can show it's close to n squared. So almost all pairs are incomparable. Then divided by the maximum number of pairs that one linear ordering can reverse, then you get a lower bound. And how that works is also quite simple. So this is a well-known result from random graphs, is that you take some alpha, that's something like this, okay? And then you take alpha n vertices here, alpha n vertices here. There must be an edge between them, no matter where those two sets of alpha n vertices are. And that's enough. So let's take any realizer and then consider one of the linear ordering there. Is it possible? Okay. So now I order the vertices in A and B according to this L. Let's say L1. So all the vertices here are smaller and going larger in A this way, and then here going larger, right? And now you take the largest alpha n elements here and the smallest alpha n elements here, and I want to ask you, if I have a non-incomparable pair x and y like this, is that linear ordering going to reverse that pair? And the answer is not, right? Because x is smaller than this, which is smaller than this because there is an edge here. And then this is less than y, so y is greater than x. So it's not going to be reversed. And that's most of the pairs. So if you count the pairs that can be reversed, then x has to be, either x has to be in this purple part or y has to be in this purple part. So immediately you know the number of reversible pairs is bounded by 2 and alpha n times n. And in total you have n squared. Then divide by this number, you get something like this. And that's the proof. Okay. The most difficult or challenging part is actually proving the upper bound. Since all the previous work was built up upon Freddie and Kahn's upper bound, which proved to be tight, but in our case, it's not tight. So recall this is some kind of literature review of known upper bounds there. So this is Freddie Kahn's upper bound in terms of maximum degree. Okay, so it's roughly speaking, it's bounded by the maximum degree. So Erdős, Kierstead, and Schroeder studied this and then proved the lower bound, roughly speaking, is maximum degree. And this is in the range where most of elements having the degree that's roughly speaking is the maximum degree. So all the vertices are about the same degree. And that's why the bound works so well. And in the sparse case, you don't expect that to happen. So most of the vertices will have degree, some constant times c. And then there are some really large ones, that's like a log n. And a lot of them are of order log n, right? A linear number of vertices will have really, really large degrees. So this is a new decomposition theorem that we just proved, sort of tailored for study random partial order set, but I feel that might be actually interesting, just in general for bounding dimension of partial order set, and we are not aware of anything like this in the literature. So what it says is the following. You take a subset of elements from A. This is a bipartite case. Think of them as the problematic elements because I'm really in trouble because there are some elements that are comparable to so many others. I select them out. And now I look at the upper set of it. And I look at the dimension of the pole set induced by these elements. And that gives me this one. And now I delete this SA from the partial order set. And I look at the dimension of the remaining elements. And that's the second one. And add them together, that gives an upper bound for the dimension. And this is tied up to constant factor, right? Because both of them are lower bound as well. OK, and then you can do the same in the other direction by looking at the down set. So you can immediately see why, the proof is easy. It's by construction. Just constructing a realizer. So I'm not going to really spend time to talk about how to interlacing these realizers to get a new realizer. But I want to briefly mention, at least at high level, why it implies that the dimension of the random partial order, graph order, should be something like constant times C here. So the thing is, I take out the set of vertices that has high degree on both sides, and then look at their. I only have one click. I look at their upper set, okay, and then I look at their down set, and I remove both of them. So I apply that previous lemma twice, and then get to the rest. And the rest now doesn't have any problematic vertices. They all have low degree, up most to 10 times C. So just apply Freddy count, I get something like C log square m C. So the only thing is to actually bound the dimension of those. Here, random graphs start to play a role because we know these vertices, even though they're small linear, like 0.1% of the, or maybe 0.01% of the vertices are in SA, but because they are a small proportion, when you look at the graph spanned by them, which means by taking the neighborhoods, they are probably not going to involve complicated structure. And that's what we try to prove. They are basically unicyclic. So take a vertex from SA, and then look at the neighborhoods and how they join each other. And they are pretty much like tree-like. Sometimes two neighborhoods can join, intersecting two vertices, but not more than that. Or they can somehow make a loop and going back to the original one. But that's it. We just prove that there are no other structures. So then we apply Brightwell's result of unicyclic partial order sets, and that's dimension 4, which adds nothing to the first one. And that's how you get the upper bound for the bipartite case. So for the general case, we also have this deterministic result. We believe that could also be useful in other occasions, but definitely should help with bounding random graph orders. What it says is something similar. You take those problematic vertices elements SL, look at the downset, look at the upset. Now it's complicated because the upset and downset can potentially intersect, right? But anyway, take them and then look at the dimension, and then you just remove S and look at the partial order induced by the rest. That's the second one. Put them together, here is an extra 2 compared to the bipartite case that we couldn't get rid of. But then that's the upper bound. So in principle, I think it should give you an idea of, in the non-bipartite case, this should also indicate that the maximum degree should give you the right guess of the dimension, because there are the number of elements having high degree means number of comparable elements, is also becoming, much, much smaller, only 1% vertices are like that. However, things a little bit complicated is because those structures start to cluster. So cluster is something like, in the bipartite case, you can think of this being, really high degree and this being high degree. The way that they interact into the neighborhood is independent. But now they are all clustered in the way that there's really, really high correlation. For instance, if you have one vertex with a large downset, then you look at any vertices that's on top of it, they all have large downset, right? And then we have to find a way to clean out the clustering structure and then realize, to find out what really needs to be proved in order to bound the dimension of this part. And that's not finished yet, but I think the intuition here is very clear that that vertices of that type, even if you take downset and upper set and look at the induced part, the dimension shouldn't be too bad. You can even apply this result several times if it induces more cycles, and then you will still be successful. So that's pretty much what we discovered, and that's the whole story so far. I think I will quickly mention some open problems. So the first thing I think I already mentioned in the talk, the research was actually inspired by causal set theory. And I'm personally very interested in sparse models because we can prove things interesting. And in the p equals a half case, it's boring. But I'm not able to really put those two consistently together because the sparse model somehow is also a little weird, the way how the random graph orders are in terms of modeling causal set theory. So that part, whether there is a way to find sparse models interesting for causal set theory, that's certainly interesting. There is a conjecture, I think it's really cool, and that's actually the one that we first started to study. When I saw this conjecture, I thought, we must be able to prove something. It's this. If you look at the partial order whose cover graph, well, I didn't define it yet, but okay, so it's just you just take the partial order and then you take the reduced graph, which means if you have I to j to k, then you don't draw I to k, right? So just a reduced graph that really represents the partial order. So if that one is a tree or a forest, then we know the dimension is at most 3. And you can actually fully characterize one is 1, one is 2, one is 3. However, whenever it has one cycle, it's not clear. I mentioned that I got a result from Brightwell because they write in the paper that it's known it's at most 5, but the reference was wrong when we tried to track down the proof because we couldn't prove it even for 5. And then I have to email Brightwell, and then he actually told me a proof that was 4. In the paper, they conjecture that it's at most 3. And again, it sounds really, really appealing, and I feel we know so much about trees. It should be possible to prove that. But because of the transitive closure, it's not really a tree. It's not really a graph. So we were not successful with this one-off. And this is also a conjecture or open problem that I mentioned earlier. So in the bipartite case, it was when the p is very, very close to 1, the dimension is still n. But then it suddenly drops to 2 in a very, very small range of p. Exactly how they drop is very interesting, and I think it has something to do with my personal feeling of somehow the containment, the perfect matchings in the complement graph, but I'm not completely sure. I haven't really thought about it, but that's a nice result here, a nice open problem here. And it's also because of the large anti-chain there, right? That makes it interesting. So in GNP, it's not that interesting, but in GNNP, it's really interesting. And then last question is really for the new decomposition theorem that we proved, is there any more applications? Because I don't really do research in that field myself, so I don't know what people study, so whether we can make use of it. I think that's all. Thank you very much.
Thank you for the talk. Any questions? Wait for the mic, please.
Thank you. You mentioning sparse models, so around C over n, is there any interest studying regular graphs? Like instead of looking at GNP, looking at the regular graphs, starting with a regular graph like around GN, like C over n, and taking the closure, and what kind of poset do we get?
I don't know. I think there are many questions to ask. Maybe dimension is one of the hardest ones. If we ever want to study other models, I guess the first thing is probably motivate why it's interesting. Some people ask about the multi-layers when I gave a talk in physics, because in random graph theory, we wouldn't think of it because it sounds not very motivating. And people even don't want to study bipartite, right? So why do you study tripartite? But now we see that bipartite is so different from GMP. It actually, for poset, it might be interesting to think about this like fixed number of layers kind of model. That might be an interesting model. Regular, usually people study that model because of several reasons. One reason is because they really want regular, but once you do closure, you definitely destroy the regularity. So that might be a reason that it's a little hard to maybe motivate the research. But if you want to keep regularity after taking closure, I think it's very hard to count.
Yeah. Thanks.
Other questions? All right, well, let's thank Jane again.
Thank you.